Originally, James Austin was invited to give a talk here. James is probably becoming a father for the first time as we speak, so I was roped in to give this talk. James has contributed the majority of the slides, and I've added quite a few. But if I go over time, I'll just blame James.
The baby.
So, Murray Hitzman is quoted here, said we will be increasingly utilising geophysical techniques. So we need better geophysical techniques and technologies, better understanding of the geophysical properties of geologic materials, both ore and waste, and integrated geophysical models of ore deposits. So I hope some of what I present today will address those issues. We have superb magnetic coverage of the Australian continent compared to almost everywhere else in the world. And the question is, how do we use it? Why it could be better? I want to talk a little bit about magnetic minerals and relationships to mineralisation, structural controls, petrophysical zonation and redox. I'll touch on that. I'd like to present just a few examples of predictive magnetic exploration models, in particular for gold-rich porphyry copper deposits, and touch a little bit on remnant susceptibility and some of the issues involved with that. So it's quite a lot of material to cover. Just a very simple illustration of simple bump hunting. Can occasionally be successful, but often isn't. In this area in the eastern succession of Mount Isa, there are bumps that are mineralised and bumps that are unmineralised, and lots of false positives. So Starr and Selwyn wasn't picked out in the magnetics originally. Cannington would probably have been missed using magnetics alone. These are barren magnetites at Lightning Creek, and over here. Osborne was targeted on magnetics originally, but because the very important effect of self-demagnetization was not recognised at the time, the initial drilling drilled down dip and missed the target. And so it took a little while to sort that out. So gravity modelling is a little bit simpler than magnetics. There's one parameter of interest, namely the density contrast. If we're going to do an inversion, we can invert the anomaly assuming a uniform density for a given body, or a smoothly varying density using a voxel inversion. And we assume a uniform gravitational field. That's not important in the sense that the gravitational field is not an inducing field, but it is important in the sense that our anomalies are always very much smaller than the Earth's overall gravity, so that we can therefore assume the local vertical is not significantly deflected when we're measuring vertical component of gravity, and therefore the gravity is a good potential field and you can do all sorts of processing. Now, that sort of assumption is also made for magnetics. In this case, the Earth's magnetic field is an inducing field, so our magnetisation is proportional to the product of the susceptibility and the Earth's field. So that's ignoring remnants, of course, which I'll come to later. And we can invert assuming uniform properties within a given body, or voxel inversion with smooth variation. And it's also assumed that the Earth's field is not deflected significantly by the anomaly, and that is not always true. The Hamersley Basin is a very good example where it is definitely not true. Also, magnetisation, it is a vector property, so it's more complex than density contrast, which is a simple scalar. And also, as well as the induced magnetisation, which is proportional to susceptibility, We have remnants, which in ancient rocks can be in almost any direction, depending on the age of the acquisition of the remnants, how far the continent has moved, the Earth's polarity at the time, and so on. So, what actually causes a magnetic anomaly is the total magnetisation, which is the vector sum of the induced magnetisation and the remnants. Now, in certain rock types, pyrrhotite-bearing massive sulfides, one example, banded iron formations are another, anisotropy is important. And that can deflect the induced magnetisation. It's no longer a simple product of a susceptibility multiplied by the Earth's field. When you have strongly magnetic rocks, self-demagnetisation can deflect the magnetisation direction away from the inducing field. There can also be interaction effects between neighbouring magnetic bodies. So all of these things complicate magnetic interpretation. So, in some cases, the assumption that all magnetisation is induced. I mean, that was always the default assumption because people just didn't know what to do about remnants and it was all put in the too hard basket. It's never entirely true, but in certain cases where you have hydrothermal magnetite, it's chemically pure end-member magnetite, it's well crystallised, fairly coarse-grained in many types of deposit. In that case, you can expect that the remnant magnetisation will be subordinate, at least to the induced magnetisation. The Königsberger ratio would typically be about 0.2 to 0.3, and most of the remnants will actually be viscous remnants. In other words, it's relaxed towards the present Earth's field direction. Therefore, it's essentially enhancing the susceptibility. So it's something that's not measured by a susceptibility meter, but it adds 20 or 30% to the effective susceptibility. Well, we believe we can do much better, or we should, we need to. Okay. So, in modelling, there are two end-member assumptions and, that are being used. The voxel inversion type approach is assuming that petrophysical properties are gradational, smooth transitions, no sharp edges, or in traditional old style of the geophysics, we assumed there were shapes in the subsurface and they had uniform properties within them, and you tried to model your anomalies that way. In reality, the Earth is actually somewhere in between those two end-member models. Okay, I want to mention something about magnetic mineralogy and what generalisations can be made about magnetisations. So ore deposits are inherently very complex systems and they're quite heterogeneous. They often contain multiple magnetic minerals which are deposited at different times. There's overprinting types of alteration with different magnetic mineralogies, and they also overprint remnants that's been acquired by earlier generations of magnetic minerals. Now, the physical factors that affect how a magnetic grain will behave include its mineralogy, chemistry, crystal structure, grain size. But these things are actually relatively well understood. So they influence the intensity of the remnant magnetisation and susceptibility, how easily the remnants can be overprinted, in other words, how easily the rock can be remagnetised, and at what temperatures it may be reset. So in any given deposit there may be multiple magnetic minerals. That's not always the case, but here's an example from Monokov that James has worked on extensively. And we can see in different zones of the deposit there are different trends. So, whoops. Sorry. So the magnetite BIF zone here, there's a linear relationship between density and magnetic susceptibility, which is just reflects the proportion of magnetite in the rock, very understandable. Within the ore zone, there's a mixture of magnetite and sulfides, and we have another trend, general trend this way, which is has a shallower slope because of a lot of the density is coming from the sulfides, not just the magnetite. In the chalcopyrite rich ore, that's even shallower still, and hematite BIF, the susceptibility is very low. The hematite contributes a lot to the density, but not much to the susceptibility. Briefly mention the issue of pyrrhotite. Once again, this is an area where James has been involved. There are two sulfide bodies here. This one, canteen, contains monoclinic pyrrhotite, which is the magnetic type. Over here, we have one that's almost invisible to magnetics because the pyrrhotite is hexagonal. Now, I don't actually know much about the specific area, but as a generalisation, I would say if you have a type of mineralisation with pyrite along with pyrrhotite, and particularly there's a bit of magnetite and plus pyrite, you will tend to get monoclinic pyrrhotite with that. Hexagonal pyrrhotite is precipitated in more reduced systems and will not generally occur with magnetite. Anyway, at this, in this area, this prospect, James has been finding stunning amounts of remnant magnetisation. The remnant magnetisation up to 1,000 amps per metre. The Königsberger ratios in some samples are up to 700, but the common and overall average value would be in the range 20 to 30. So basically, nearly all the anomalies coming from remnants and not from induced magnetisation. Now, when you have monoclinic pyrrhotite as your sole magnetic mineral, you will always get a Königsberger ratio greater than 1. Typically, for very coarse-grained pyrrhotite, 2, 3, or up to 5, say. For fine-grained pyrrhotite, a few microns in size are much higher, 50 to 100, or sometimes even higher. Okay? And the magnetisation, the remnant magnetisation of monoclinic pyrrhotite reflects the latest thermal event in that area, basically, because it's reset by heating above 320 degrees C. So in most areas, the remnant's direction is that recorded when the area last cooled through 300 odd degrees. What do we find when we measure lots of susceptibilities within ore zones and alteration halos and in the background in the host rocks? Is you get a lot of variability, fine-scale variability, which of course you cannot see when in the magnetic anomaly. It's just an example of the sorts of variability you can get, and what James has done here is put moving average through there to get a better idea of the characteristic changes. And the point I think here is that even these systems where magnetic minerals are associated with, in a general way with the mineralisation, the actual area of the most highly mineralised area may not be the most magnetic. So here we have the area of high mineralisation but relatively low magnetic susceptibility is a massive pyrrhotite zone. And just an illustration of the complexity in having in certain systems, particularly iron oxide copper gold systems, is there are multiple generations of alteration, some of which are magnetite producing and others of which are magnetite destructive. However, there's a crude generalisation in these magnetite rich ASEG systems. The early regional, semi-regional sodic alteration is magnetite producing, sodic calcic. Also, then the somewhat higher level potassic alteration also tends to be magnetite producing. And the upper levels of the system, The later stages of alteration, HSCC and so on, alteration, are magnetite destructive and hematite producing. So it tends to be a general zonation in these systems, which is a useful thing to realise when you're trying to model these systems. So, turning to the Olympic dam type of system, because of the great density of the hematite, they're associated with very large gravity anomalies typically. They generally also have magnetic anomalies. These can be quite subtle because if the upper levels of the system are still intact, as they are at Olympic Dam, the hematite is weakly magnetic and the magnetite is deeper and peripheral to the main hematite zone. So people tend to talk in these systems about coincident magnetic and gravity anomalies. I think that's a misnomer. And in particular, say, the Olympic Dam deposit, it's inferred to have formed at very shallow depths. It's dominated by sericite, hematite, quartz, chlorite, siderite, etc., alteration. And magnetite's been totally replaced by hematite in the central and upper portions of the deposit, but it is present in deeper and peripheral zones. And as I mentioned, ASEG systems tend to be zoned vertically from magnetite dominant at depths to hematite dominant at upper levels, and magnetite may also be abundant peripheral to the ore zones. So what does that mean for the gravity and magnetic anomalies? Magnetic and gravity signatures of complete intact ASEG deposits of this type should generally reflect superposed gravity and magnetic anomalies. So the gravity anomalies arise both from magnetite-rich and hematite-rich zones, whereas the deeper peripheral or in some cases adjacent magnetite sources correspond to the magnetite-rich zones. So the inverted centre of magnetisation lies beneath the centre of mass. So they're superposed, not coincident. And if you get post-mineralisation faulting or tilting, that can modify the signature and give rise to juxtaposed gravity and magnetic anomalies. And I'm suggesting as a possible example of where this has happened is a prominent hill. Here you can see the gravity anomalies here, superimposed on the ground magnetics. So there's a strong, if you like, coincident gravity and magnetic anomaly here corresponding to a magnetite-rich zone. There's a fault going through here, but the mineralisation is very similar to Olympic Dam. It's in the hematite breccias through here, and there's only a very subtle magnetic signature through there. This shows the regional context through here. So if we zoom in on here, this is the magnetic anomaly that also has a gravity high. Very subtle magnetic anomaly. There's a gravity high through here, and this is the fault that I think is one of the faults separating these two zones. So there are people here who've actually worked in this area who can tell me I'm wrong, but my naive interpretation is that up here we're looking at an originally deeper part of the system that has been up-faulted, and so we now have juxtaposed magnetic and gravity signatures. So turning to Einstein-hosted deposits, these generally cause narrow elongated anomalies, which can be modelled as subvertical sheets or elongated elliptical prisms. They have high density, but in some cases, for instance at Monikoff, it's basically the volume isn't sufficient to really produce a strong gravity signature. And in this case, we have it's laterally zoned with magnetite plus or minus sulfides in the core and hematite distal. The Brumby deposit that James has worked on extensively is a Bullseye magnetic anomaly coinciding with a gravity anomaly. They can be modelled as pipes at the intersection of faults or within fault jogs. For example, Ernest Henry. And the sulphides, in this case, in most of these deposits, both formed at the same time as magnetite, and also a later generation overprints the oxides via a later alteration event. The study that we published originally, recently from La Candelaria in Chile, we were able to explain the rather complex magnetic anomaly there, not by remnants as was suggested by Graham Taylor some years ago, but by the geometry of the sheets, their self-demagnetization, their shallow dipping mantos, and interactions between those sheets. So in this case, the somewhat odd shape of the anomaly, particularly if you take into account the regional context, which is a very highly magnetic area, it doesn't require remnants to explain it. However, within the deposit itself, the remnants is about 20 to 30% of the induced magnetisation, and it has both polarities, which is very interesting because this deposit supposedly formed during the Cretaceous normal normal polarity interval, which suggests that it should only have one polarity of magnetisation. So this shows that there has been a much later overprinting event in this deposit, which I think is younger than 80 million years, whereas the mineralisation is thought to be about 118 million years. The remnants directions are in fact rotated substantially from the north-south direction, which they should be if they were of Cretaceous age, and that shows that this area has been rotated clockwise through about 45 degrees, as was suggested by Graham Taylor. So we think we got that right. Tennant Creek deposits great targets. They're small, but they were very rich, very high grade, and nice deep targets could be modelled as ellipsoidal bodies, and if you did that and took into account self-demagnetization, you could generally hit your target. The ellipsoid model is very appropriate in this case because they are syn-deformational, mineralisation is syn-deformational, and the bodies are flattened in the cleavage plane and elongated along the direction of maximum extension. So the geometry works very well, and the ellipsoid model is very convenient for taking self-demagnetization into account. Okay. So these range from more reduced type mineralizing fluids to more oxidized types. So as you go from magnetite plus pyrrhotite through to magnetite dominant with some hematite, a little bit of pyrrhotite, through to magnetite plus hematite, you get a reduction in the amplitude of the magnetic anomalies along here, but similar gravity anomalies. Okay. So, in a sense, the ratio of these two anomalies can tell you something about the nature of the system. It's redox state. Okay. How am I going for time, actually?
Another 5 minutes?
Yeah. This is something I wanted to get into because it involves forward modelling, pretty old-fashioned forward modelling. So in an Elmira project, P700 some years ago produced a lot of predictive magnetic exploration models for porphyry copper and iron oxide copper gold deposits, and just take one example, which is the gold-rich porphyry copper model, and this is based upon the Bajo del Alumbrera deposit in Argentina, which I sampled and actually had pretty decent petrophysical data from. And this is a nice intact vertical system that's emplaced into mafic or intermediate volcanics that are quite magnetic, and we can calculate what would happen with a system like this if it was emplaced and there's been no erosion, uplift and erosion since, or if we've removed various amounts off the top of the system to expose different amounts of the body. So this makes a tremendous difference in the expected signature. And one of the points of this modelling is to look for the correct, appropriate signature in the local geological setting. If you have a nice signature over a known deposit, it's a mistake to go looking for a similar signature elsewhere in your area where the host rocks are different, or if the level of exposure is different, or if it's buried deeper and all the rest of it. There's magnetic volcanics over the top of it. This sort of approach, you can actually work out what the signature should look like in a semi-quantitative way at least. So you can see if the deposit hasn't been uplifted or eroded at all, you actually have a broad magnetic lobe. As you remove more material, you get an archery target signature, and then basically once you're deeper in the system, you will get a big magnetic high. This is reduced to the pole, so it doesn't matter about where you are in principle. And that's associated with the fairly juicy mineralised copper-gold mineralised zone associated with the potassic alteration, which is very biotite, magnetite, plus or minus K feldspar. That's the actual signature of Alhambra, which the image is courtesy of Terry Hoschke. This is the signature of the potassic zone. Here is magnetite destructive alteration associated with the philic alteration. Then we go out into the propylitic, which where it's strong is somewhat magnetite destructive, where it's weak it's magnetite stable, and then you get back to the sort of noisy signature of the unaltered andesitic volcanics. It's just a beautiful image. Now, the reason why this system, fits a model so well is because it's still upright. It's had a little bit of top removed, but the system is still intact. It hasn't been faulted or tilted or whatever. But the signature will depend on the host rocks. If you place it into felsic volcanics or quartzites or whatever, the signature changes dramatically. Okay, so we've got andesite host, like we have it on Rara, felsic host, carbonate host, where you get skarns, skarn signatures generated around the outside and adjacent to it, and quartzite host, where quartzites are very unreactive, so you see absolutely nothing in them, unlike in carbonates, for example, or in mafic volcanics. The signature depends on magma type and tectonic settings. So I've shown here the difference between high potassium systems and less potassic systems. And the high K systems are those typically in island arcs. They're more oxidised, they're more mafic on average. You find them typically in island arcs. Or they're more alkalic systems in continental arcs. So high K calc-alkaline to shoshonitic, whereas there's less development of a potassic alteration zone with magnetite, where you have low potassium or low to medium calc-alkalic systems in continental settings, particularly with thick continental crust, such as the laramide porphyries. Dramatic effect if there's post-emplacement modification of the deposit. It's actually quite common for deposits to be tilted. In the original Lowell Gilbert porphyry copper model was actually based upon two ore bodies that were originally one system and were faulted and tilted, and tilted at an angle rather similar to what's shown here. Okay. So the signature goes from this, where you have the central low due to its low, it's a deep body and there's a lot of magnetite destructive alteration on top and around. But when you tilt the system, the signature changes completely. So you need to take these sorts of things into account in your local geological setting to see what the sort of signature you might find. And of course, signatures vary if your system is in place along a lithological contact, because you get asymmetric alteration patterns and so on.
2 minutes, Dave?
Okay. So the conclusions about that is the magma type and tectonic setting are important, host lithology, current level of exposure, depth of burial beneath the undercover, and the nature of that cover. Post-emplacement tilting and or faulting, and asymmetric zoning if been placed on a lithological contact. But let's not despair. These effects are reasonably predictable, at least in a semi-quantitative way. And so they must be considered if to search for the appropriate signatures. And another implication is searching for lookalikes of a known deposit is unlikely to be successful if the local geological setting differs. So I might skip through this because I have mentioned some of these effects already. I just wanted to point out the very strong effect of grain size on magnetic properties. Magnetite grains that are tens of microns or larger are multi-domain, strongly multi-domain, and they tend to have relatively weak and relatively soft remnants. So the remnants they have is largely viscous and adds to the effective susceptibility. When the grain size is a few microns, they're pseudo-single domain, and when it's even smaller, they're single domain, and these have retain strong, stable, ancient remnants. Okay. I don't think I've got time to go into that. So, what happens is when multi-domain rocks are drilled, they often acquire very soft drilling-induced magnetisation along the drill core. That's completely unrepresentative of the in-situ magnetisation, but the good news is that can be removed very easily by very simple techniques like liquid nitrogen treatment. Knocks down this magnetisation here. Now we have the rest of the magnetisation here, and you could extrapolate that the in-situ magnetisation is around about this level and not way up here. Okay, so that's one. And alternating field demagnetisation is another way to get rid of this noise, which is unrepresentative. The point of this slide is to show that. Some magnetic lows are not always due to remnants, so they can often be just due to magnetisation contrasts. Here's an example where there's an extremely strong and stable remnant magnetisation at Mount Harkis. This is in the Giles complex in Musgraves. And it's a very interesting occurrence. What we have here is actually ilmenohematite that has undergone deuteric reduction and produced very fine-grained magnetite in it. And this has produced an incredibly strong magnetisation. And these are the sorts of things that you can see in other bodies that have been studied around the world. In fact, the samples from Mount Harkis have been sent to Suzanne McEnroe, who's sort of the guru on this type of magnetisation, and she's looking at them right now. And that's just to show that the direction of magnetisation is ancient and not parallel to the Earth's field. Those are downward pointing inclinations to the northwest. Okay, these are drilling-induced things that are uphole and soft. And if you do use that direction of magnetisation for your RTP, you get a much better understanding of the geology than if you just did an RTP assuming induced magnetisation. So that's just an example of what you can do if you know a little bit about the magnetisation history of the deposit. I think you want me to wind up. Yeah, okay. I'll just let you read the conclusions.
Great, thanks, Dave.